Hello everyone, my name is Roy Jafari, and in this video we are going to talk about clustering. Clustering is one of the data mining tasks that is called unsupervised, and as you know, unsupervised tasks are the one that you don't have a specific goal for the data mining task you're performing. Clustering is merely looking at the patterns in the data and see if the data objects in the data can form a meaningful clusters on their own based on the attributes. There are many concepts and algorithms that goes with clusterings. In this video, we're going to talk about a few of them. We're going to talk about the concept of clusterability and the H and the Hopkins index to see if our data is clusterable, and also we're going to be using K-means algorithm to perform a clustering task, and also we will see some techniques as far as how we would go about finding the number of clusters in our data using K-means and other metrics that we will get introduced to in this video. So it's going to be a bunch of different concepts that we will learn around using the World Happiness Report dataset. Now, this dataset is a dataset that I've already taken the time to pre-process, and it's ready. There is no missing value or any other issues. And I'm going to share that version of the dataset with you so you can just practice clustering with it. All right, so let's get to it. Alright, so we're going to be using K-means, as I said, as our clustering algorithm. And K-means is, the most famous and most applied clustering algorithm. So that's one we're going to be using as well. So here we are importing the modules, that are, basic modules. And once we want to, use a function for clustering, I'm going to import that then so we can talk about it. This is the pre-processed data that I just talked about. If you look at this data, let me grab these for a second and put them here. If you look at this data, you will see this data comes with, name, continent, year, population, life ladder, and so on and so forth. But for this video, for this session, we only want to focus on 1 year of data because, having so many years of data, it requires some other data pre-processing that's just going to take it away from our goal of learning clustering in this video. So I'm just going to focus on the year 2019, and I'm just going to also use the happiness indexes, the ones that are about the happiness of those countries. I'm not going to take into account continent and the population. So to do this, I have done some pre-processing here. I just say I want to have only the year 2019, use a Boolean mask, and just keep those that are not in this data set, and then drop the columns year and change the column name into the index of this report df. So once you run this, you will have a data set that doesn't have that year, and also every row of this data frame is a country and the columns are describing this country. But we want to only use the happiness index to do this clustering. So I only use these select columns. These are the happiness indexes. It's life ladder, log of GDP per capita, social support, healthy life expectancy at birth, freedom to make life choices, generosity, perception of corruption, positive affect, and negative affect. And I'm using only these to form my X's or my attributes that I'm going to be using for clustering. Now pay attention here. One of the very important steps you need to take before doing clustering on any data is to either standardize or normalize your data. And the reason is clustering uses the distance between the data objects that are calculated based on the attributes of the data objects, right? And if one attribute has more has a higher range, or its scale is just more than the other attribute, it's going to consume the space of clustering, space of distance, and you'll be basically, in effect, will be clustering your algorithm based on the attributes that have more range, or have are presented in a higher scale. To avoid that, you always want to normalize your data, and the way I have just done this, I normalize my data. So this is the data that you can see. All of them are from minimum and maximum 0 to 1. Now this is the data that you can use for clustering. So before we actually perform the k-means on this data, we have to also pay attention if our data is clusterable at all. I mean, if you run the clustering algorithm on any data, it's going to spit out or output some clusters, right? So that's what it does. It goes through its algorithm. It doesn't have a memory or an intelligence to tell you, hey, this data is not clusterable, and what I'm giving you is merely random. Because if your data is not clusterable, what KNN will output, what k-means will output, is just a random grouping of your data. But if your data is clusterable, that means that there are meaningful groups in your data, then k-means probably would find those groups. So we have to check our data clusterability, and one of the ways you can do this is by using Hopkins statistics. Hopkins statistics uses a randomized way of going about seeing if there are meaningful clusters in your data. Basically, it compare the distance of some randomly selected points from your data object to the rest of the data, and also some randomly created points in the space of your data. So these are the two different things, right? And then uses that distance between them to see if your data is clusterable. So I haven't come across any good module that actually calculate this. I came up with it myself. But if you're watching this video and if you know that module or know that function that I can just import and use it, please let me know. Put in the comment or something, and I'd be happy to start using it as well, and I'd be very thankful. But for now, we don't have it, so I have created it myself. And the Hopkins statistics takes the data and also the number of random points you want to be selecting. And the higher the number of data objects that you have, here we have only 122 countries. The bigger the M can be, and also if the M is too large, it might lead to some computational complexity, computational cost, or your runtime will be higher. So here we're just using M10. I think that's enough for 122 data object, and we just calculate the Hopkins statistics. And Hopkins statistics is 67. As you remember, I said Hopkins statistics does calculate its value randomly, right? So if you run this a few times, you will get a different value. So let's go ahead and run this 20 times with the loop, right? So we run this 20 times and we see it's always greater than 0.6, and it sometimes even reaches 0.75. And if we know if the value of Hopkins is greater than 0.5, that means you have meaningful cluster. So our data is meaningfully clusterable, and the clusterability of our data is proven using Hopkins statistics. So now that we know this, we can go ahead and import the k-means module from k-means, the sklearn.cluster module, and use this function to cluster the data. By now that applying the actual algorithms on the data is very simple. It's just 1 or 2 lines of code. Preparing the data for the algorithm, and also knowing if we are doing it in the right way, and then interpreting it is the real thing that we need to learn how to do the best we can. So like I said, running it, you just say, okay, I want 4 number of clusters, something that we will discuss. How many clusters we have in this data, we will have to figure that out. but we just just put a number here, 4 number cluster, and then fit to our data that it will be randomized. So once you run this, you will get 4 clusters with different country names, right? So this is just, we just did this, and our data are grouped together, and we do know that our data is clusterable. So there must be some meaningful relationship between these clusters. Another way you could check the clusterability of your data is by checking the consistency of your output of K-means, right? So if your data is meaningfully clusterable, every time K-means go through the data and groups the data, if they are meaningfully clusterable, the output of these runs are going to be the same. We know that K-means is also a random heuristic for clustering. So if a random heuristic reaches the same conclusion every time, or reaches to similar conclusions every time, there must be some meaningful relationship for clusterability of our data. So that's another way we can go about this. So for us to be able to use K-means as a way to check the clusterability of our data, what do we need to be able to do? We need to be able to, within a code, be able to compare the output of these different runs of K-means. And there are different ways you can go about this, but one of them is doing it by comparing the clustering using counting pairs, and then using counting pairs to come up with a metric that I have created here. So counting pairs is basically, let me go ahead and run this. Counting pairs is basically telling you whether the pair one-to-one relationship between clusterings on one clustering to another, right? So you have one clustering of your data, you have another clustering of the same data, and it says, okay, each of these two of the data objects, are they in the same cluster or not? These two are in the same cluster, these two are not in the same cluster, neither of them are in the same cluster, and the possibilities of all the pairs are in your data object. So like I said, the counting pairs also is not a module or a function that I've been able to find. So if you have found it, if you know a module that can do this, please also comment, let me know so I can use that as well. So here's the function I've created. So if you run this with some random clustering, so this is not a K-means clustering, this is randomly created cluster. We're just randomly creating a number between 1 and 4, and second time we are randomly creating numbers between 1 and 19, and we're just seeing their counting pairs. It says that out of all the pairs in this data, we have 33 of the possible pairs not in the same cluster, and 0, 0, that's what that means. And then in the clustering on the right, or the second clustering, none of them are in the same cluster. In the clustering on the left, in the first clustering, and that makes sense because there are less number of cluster, 12 of them are in the same cluster, and none of the pairs, possible pairs, are in the same cluster for these clusterings. And that makes sense. I mean, we just did this randomly. It would make sense for them not to have that much relationship with one another. So we could eyeball every time and see the relationship between our clusterings, but we could also use these for creating a metric. There is a metric you can be using. It's Folks-Mallows metrics that is famous in the literature. We can be using it here as well. Basically, it gives us a number between 0 and 0.5. The closer the number is to 0, the less the clusterings are similar, and the higher the numbers are to 0.5, the more similar the clusterings. So here, after creating the Folks-Mallow, we see that when we do randomly create clusters, the values are not that high, and we see it changes from values from 0.08 to 0.2. Let's go ahead and sort of experiment with Folks-Mallow with some randomly created clusterings and see the range of the values. So we do this in a randomly create clusters, and we see that the values could range from 0 to actually 0.1 to 0.2 at times. But let's go ahead and actually change this into the number of data objects that we have here, because that will change these values, right? So let's go ahead and change it, and we can see that the cluster, the numbers are a little bit smaller, right? So for these number of data objects, we would, if we saw numbers like 0.12, 0.2, that wouldn't be that impressive for Hopkins, because we randomly created two clusters and these are the numbers we get. So if we get closer to 0.4, 0.5, that's when we would know that the similarity between these clusterings are meaningful and high. So now we have this capability. Let us also check if our Folks model is working. If we said clustering 1 and clustering 1, basically these are the same clustering, so it should give us the highest possible number. And once we run this, it does give us the 0.5. So now we are at the point that we do have the programming capability to run different K-means clustering on our data and check if they are giving us the same output or similar output. So we do this here just one time with the same number of clusters, and we see it gives us 0.5. It means that meaningfully these clusters are the same, right? And that's a good news, because K-means is a random algorithm, and it goes through the data and find these clusters based on a heuristic algorithm. And then, since these are the same, so it means there is meaningful relationship in our data that forms groups. So let's do this for 20 times and see if it changes. For the most part, it's reaching the same number of clusters, the same clusters, but sometimes it doesn't. And that's something we will keep in mind, that K-means is not always capable of reaching that meaningful cluster. So we'll keep that in mind. But the next thing we need to focus on here is how do we know how many clusters are in the data? And there are many different ways you can go about this. There are many different methods, and none of them are perfect. In fact, none of them are perfect. I mean, it's the trickiest part of performing clustering on your data. Sometimes one of these methods, some of these methods gives you a really good answer right there in front of your face. You can just pick, and sometimes the answers is not that easy, and it just depends on the data. We go over two of these methods to see how these methods can look like, and also sort of like think about, or go over them and think out loud on how do we end up choosing the number that we choose for the number of clusters. So the first method is doing it by sum of squared error, SSE. Basically, SSE is a value of each of the data objects from the centroid of its cluster, and the lower this number is for all of the data, right, the better your clustering. But the trickiest thing about SSE is if you have more clusters, this value is going to be lower. If you have 3 clusters, this value is going to be lower than if you have 2 clusters. So you will actually see, so we are going to computationally calculate this SSE for when your clusters is, you have 2 clusters all the way to 14 clusters. And since K-means is a random algorithm, we repeat this 10 times for each of these number of clusters. And then we do the clustering, and then we calculate that SSE. Actually, the algorithm does it for us, so we only need to grab it from the fitted model. And if you get the dot inertia underscore, it'll give you the sum of squared, and we just see which one. I mean, we just see the pattern in the decrease of the sum of squared error. So let's just go ahead and run this, and once we have that, figure, we will talk about it. All right, so it was fast enough. We have the mean and variation. We can see that, as we come from 2 cluster going down, we are improving our SSE. And, I just talked about how it should be expected. The less number of clusters you have, the more compactness, the higher number of clusters you have, the more compactness in your groups. Therefore, SSE is going to be lower. But, the way you can actually use SSE is actually by creating this plot that gives you the the SSE or the mean of SSE on different repetition. If your clustering algorithm that you're using is random, like K-means, you will have to find the elbow in your figure, right? So the elbow is the one that the amount of decrease in your decrease of your improving the SSE, suddenly the amount of it became lower. So here from 2 to 3, we decrease more than what we decrease from 3 to 4. And this is the sign that probably based on this way of looking at this, we should go with 3 clusterings. We do also have a very slight elbow on number of 7, but the elbow that we have here is much more prominent, and we can just see it with our eyes. So we keep this in mind. With SSE, there was somewhat an elbow on k equal to 3. There's another method we can go about. This is very similar to the previous method. This time, instead of using SSE, which is a metric for the compactness of your cluster, is we are going to be using silhouette score. Silhouette score includes the compactness of the cluster, but at the same time, how different these clusters are from one another. So it has 2 sort of concept inside this metric that is helping us figure this out. Since it's been engineered in a way that you look at the compactness of your cluster, at the same time how far away these clusters are from one another, the higher the silhouette score, the better. So it's not like SSE. It's if you reach a higher silhouette score, normally we would say it's a better clustering than not. So we do the same thing. We import the silhouette score, and then we see, the way we calculate the silhouette score is that we pass the data and we say, okay, what was the data labeled, or what are your clusters, and it spit out the value of the silhouette score for us. So let's go ahead and run this and check from clusters 2 to 15 and check if the silhouette scores are going to be better with any of these clusters. So let's go ahead and run this. Let's just look at the result. Okay, we do see that the silhouette scores actually drops as we increase the number of clusters. There is one increase here at 10. It could be something meaningful, we could check. But another things you want to think about when you form clusters is too many clusters are going to be overwhelming. I mean, at the end of the day, we want to look at the output of these clusterings and make something off of it. I mean, if you have too many clusters, it's overwhelming for us. Then at the same time, by looking at this, you should split our data into 2 clusters, and 2 is just like not enough to capture what's happening in the data. So based on looking at these 2 methods, I would say it's better to use 3 as the number of clusters, because there is clearly something here, and even though it's we are not seeing a lot of improvement as we go from 2 to 3, we would see if we saw that if it was going to improve it significantly, we would see a better silhouette. I mean, I have seen silhouette score that if you go from 2 to 3, you actually improve it with different data sets, of course. But let's just go ahead and use 3. So now that we know that we want to use K as 3, now we want to check if our algorithms can find those clusterings with 3 clusters every time. So once we run this, we see there are cases that the clusters that are found based on 3 number of clusters are a little bit different. So now that we do know that this might happen, we have to make sure that we capture the one clustering that is better. I mean, like every time KMeans run this, it might be a clustering that is more meaningful, and this might be the clustering that it happened that not to be able to find the meaningful clustering in that time. So we want to guard ourselves against the randomness of K-means. And how we go about this, we use random state. I mean, we identify the randomization or give them identity, and then pick that randomization next time we actually want to use the result. So we run the algorithm based on different randomization, and we put them in a similarity matrix, and we see, pay attention that the rows and the columns are the same. So we would expect to see for clustering 1 the same value here, right? We would expect to see the Fox-Mallow 0.5 because they're the same clusterings. But from clustering 2 and clustering 1, when we have the Fox-Mallow 0.5, it means they're the same clustering, but K-means reach them with different randomization. So let's go ahead and use Seaborn Heatmap to see what's happening here. So basically what's happening here, we can see that K-means reaches 2 clusterings, 2 sets of clusterings, and we have to select one of them. I mean, we can see it's either a group that's the one that clustering 1, 2, 5, and 6 reaches, or clustering 3, 4, 7, 8, 9, and 10 reaches, right? So how do we know which one is better? So we can use this heuristic that if K-means reaches one of them more often, probably that one is better. So we're going to use that one. Also, we could have extracted these 2 and checked their silhouette score and pick the one that has better silhouette score. That could have been another approach. Here, we're just going to use the one that happens more often. So the clustering 3, if we chose that one, it's going to give us that clustering that we think is more meaningful. So the clustering 3 is created by the index random state, or the index 2, right? So 0, 1, 2. That's why we put clustering 2 here, and these are the members of our our clusters basically. So we have cluster 0, cluster 1, and cluster 2, and these are the different countries that are grouped together based on their happiness score. So now that we have this, now we want to sort of see what made these data objects to be grouped in these clusters. We can use something we call centroid analysis. Basically, we create one representative for each of these clusters. And by how do we do this? We calculate the mean of each cluster per each attribute, right? So for each of these clusters, we're going to have a representative or a centroid of these clusters. So it's some calculation that we do. This is that calculation, but pay attention here. I am creating a centroid based on the original value and not standardized or not normalized. Pay attention, I'm using report df. And also I'm creating one that is about the normalized, from the normalized one. So I call it centroid standardized. So once I run this, I have printed out the centroids for original values. I can see, their population, the mean of the population of these clusters, and also each of these scores. So I could be looking at this and see, for example, cluster 1, cluster 2 has higher generosity than cluster 0 and 1, right? But it's even easier to do this using a heat map. And for us to use the heat map, we have to use the centroid standardized. So let me go ahead and run this, and the centroid will give us a very good visual for us to see the difference between these clusters. If we look at these clusters, we will see that cluster 2 is the cluster that majorly the countries are happy. You can see life ladder, GDP per capita, social support, healthy life expectancy, freedom to make choices, generosity, perception of corruption, positive affect, and negative affect. This is the cluster that all of these values are the best among the other clusters. And then we have another cluster that is not very high in neither of these, and also is very high in the perception of corruption. And then you have another clustering that is somewhat high, but it also has a high perception of corruption, right? And the generosity is also the lowest one. So we could give names to these clusters. So these are the names I have given these clusters. So I'm calling cluster 0 happy and crime ridden, because the perception of corruption is actually the highest among them. And then we have cluster 1 unhappy and crime ridden, right? So it's not that they're not crime ridden, but it's also that they're unhappy but also crime ridden. And then we have the cluster that they're very happy. So we replace those numbers 0, 1, 2 by this function that replace, and we just create a new column in our data. We call it cluster, right? So these are the clusters of all of these data objects. So once we did this, we could do more analysis. Remember, when we started this clustering, we didn't use the continent and population for doing this clustering. I mean, these are not the values that we used for creating this cluster. So it would be interesting to see if these values that we did not use to create the cluster have relationship with this cluster. So we can see the relationship between the continent and the cluster and see if there is a meaningful relationship there. And how do we do this? We use contingency table, as we have discussed before. So I'm going to create a contingency table for the cluster and the continent, and I do see that there is a relationship here. If there were no relationship, we would be seeing the same color here. We wouldn't be seeing the change of the colors. So basically, we see the countries in Oceania, all of the countries in Oceania, a good number of countries in Europe, and some countries in South America, and some countries in North America and Asia are very happy. And most of the unhappy and crime-ridden countries are either in Africa or Asia, some also in North America, and then happy and crime-ridden, some of them are in Asia. A good part of the Europe is in the happy and crime-ridden, also North America and also South America. So we do so there is a relationship between happiness and the continent. We could also transpose this visual to see the relationship from the other side. I mean, we have summed these values based on each of these columns. So let's look at it from the other angle. And we do see that, the very happy countries are mostly in Europe, and the unhappy and crime-ridden are mostly in Africa, and happy and crime-ridden are majority are in Europe. So Europe, we either have very happy or happy and crime-ridden. We can also look at the relationship between these clusters that we create and the population. Since the cluster is a categorical attribute here, and population is numerical, we have to discretize the population before we can see the relationship between them. So here's how we have done it. We have discretized based on the 10 bins of our population, and then we create this contingency table and using Heatmap. And we do see that, again, there is somewhat of a relationship, specifically when the population is between 200, around 300 to 400 million. All of them are very happy. It could be just a fluke in the data because, you know, it's we chose 10 bins and we only have 4. So probably there is a very large gap or some outliers in the data that has led to this visual, and the existence of this outlier probably are creating this visual not to be usable. So how do we do this? We can sort of like do it from another way. So we have to be a little bit creative to do this. So let me go ahead and run this, and then I'll show you what was the creativity that led to this visual. So now we can see that in this one, you know, the happy and crime-ridden countries are, you know, somewhat similar to unhappy and crime-ridden and very happy. You know, perhaps this one value, do you see, was selected for this one. That's what's happening. So there is no meaningful relationship between the population and the cluster actually. So how did I create this visual? All I did, I added an element of randomness to the clustering. So if I were to, you know, let me copy this here so I don't lose it. Let me change this by just doing the scatter plot of the population and these members, and let's run this. Now these are all dots, right? So how many dots are here? I mean, I can't see it because they're all on top of each other, because the members are either 0, 1, or 2, right? So that's why it's not helpful. So the way I have sort of like changed this visual so it has some functionality for my analysis is I have added a random element to this visual, but so there would be, like, you know, they would be shown a little bit scattered, so I can see actually how many data objects are there, and that's what I've done. And now we can see that there is no meaningful relationship between the clusters that we found and the population. Alright, so in this video we covered a bunch of different concepts about clustering. We talked about clusterability, we used Hopkins statistics, we also used clustering consistency to see if our data is clusterable, and then we use K-means, and also we find number of clusters to cluster word happiness data. And then we did some centroid analysis and profiling on data to see if, you know, the clustering that we have created have meaningful, you know, understanding for us, that we somehow know about the space of this data set that we have created. And we did see that there were some very meaningful patterns that came out of it, and we could relate to them.